Welcome to this lesson, Introduction to Graph Databases. In this activity, we will learn about NoSQL Graph databases and compare their advantages and limitations to SQL relational databases. By this time, you have likely noticed three continuing themes in our study of NoSQL technologies. One is the emphasis on tools that scale better than a SQL database for dealing with vast quantities of data. A second is the emphasis on tools that can adeptly handle types of processing and analysis that are challenging, unwieldy, or simply impractical using the capabilities of a SQL tool. The third is an emphasis on schemaless or highly flexible and variable schema, which means we do not have to go back to the drawing board each time we need to evolve the database schema. We do not have to migrate all data to a new schema in order to make a schema change and to begin to benefit from it. You have likely also noticed that no individual SQL solution entirely replaces SQL relational databases, and that each seems to introduce its own set of limitations as well as its own unique advantages. This is a clear reminder that NoSQL does not mean we will use NoSQL relational technologies, but that NO stands for not only, and that solving today's big data challenges means that we need more tools in our data management toolbox. Yes, SQL, but not only SQL. Graph databases are a superb example of all these facts. Graph databases differ from SQL databases in that they are not table-oriented, but similar in that they also model entities and the relationship between them. In a graph database, each datum is an entity in its own right, known as a node. Instead of modeling the relationship between entities within a table, the relationship between nodes is modeled as an edge in a simple network diagram. This approach is excellent when there may be large numbers of rich and varied possible relationships between entities, when relationships may come and go quickly, and when there isn't necessarily a high degree of consistency of relationship between nodes. For example, imagine that you have 1 million entities of type A and 1 million entities of type B, but perhaps only 1,000 pairs of nodes A and B have a particular relationship. Imagine how inefficient it would be to create relational database tables for A and B when the relationship being modeled is so comparatively infrequent. Think how problematic this would be as a primary key to foreign key relationship in SQL. Now imagine that there are 500 other kinds of relationships that can exist between A and B, and that only a small percentage of nodes A and B have any one particular relationship. As you might imagine, a SQL, which is to say relational DBMS model, of this would likely end up with two tables with many columns and key relationships, or else would be normalized into a schema with many tables. Now think about what happens when you have a normalized database with many tables and you need to do a coordinated analysis or consolidated report. You have to join tables. In SQL, joins are costly and degrade performance. In a highly normalized model with only a few joins, this is usually not a concern, but with vast amounts of data, or when many joins are needed, query performance stalls, and power-hungry and long-running queries begin to tax system resources and degrade overall performance. In contrast, a graph database performs no joins. System resources are consumed for each node and each relation, but no system resources are expended when no relation between two nodes exists. This means that the relatively high cost of joins is not incurred when querying a graph database. In modeling a SQL database, we invest enormous upfront time and effort to ensure that a schema is at least third normal form. For example, schema normalization in a SQL system would require that we resolve many-to-many relationships by adding a new bridging table, also known as an associative entity. We even have a special name for such entities when an instance of an entity could not exist without the presence of the related entities on which it depends. We call this a weak entity. In other words, its sole purpose for existing is to resolve a complex and inefficient many-to-many relationship into a pair of one-to-many relationships. Significant changes in the schema, for example, introducing new entities and relations, require redesign and usually some migration or modification of data in order to ensure that all required key values are present. In comparison, new entities may be introduced ad hoc in a graph database, and additional and new relationships asserted at will, and deleted when they need to be dissolved, with no impact to required relationships and constraints found in SQL systems. Many-to-many relationships in graph databases do not add excessive burden to system resources for performance. Each additional relation between nodes simply adds incrementally to system loading and performance burden. Here's a great example of the kind of query that is actually really simple to write for a graph database once you learn the query language, but is quite complex and time-consuming to replicate in a SQL database. Which crew members love other crew members who eat pretzels? So here we are in the Neo4j console, and we've got our visualization engine turned on. And I've loaded a little database, and our yellow nodes, and they're selected yellow arbitrarily. The colors are just random unless you control the visualization engine. It just color codes like nodes. So yellow nodes here are all crew members. So Cypher is a crew member, Morpheus is a crew member, Trinity and Neo are crew members. The matrix, that's Agent Smith, and the architect, and then food items, and this blue color are pretzels and peanut butter. And we've modeled the relationships between these. So Agent Smith was coded by the architect. Cypher knows Agent Smith, Morpheus knows Cypher, Morpheus knows Trinity, Neo knows Morpheus, Neo loves Trinity, Trinity eats pretzels, and Neo eats peanut butter. And so here we can see one of the types of questions or queries that is really easy to ask in a database that is a graph database or a network database that is much more complex and sometimes kind of difficult to code in a relational database, and that is a chained question of relationality. So who has some relationship with who has some relationship with who? And so let's ask a question of that kind. So I've composed it in the Neo4j language, and here we're looking to match someone who eats food, who is a member of the crew, who is loved by another member of the crew, where the food in question is pretzels. And when you've got all that, Mr. Neo4j, come back and tell me who the person is, the loves relationship, the other person who's involved, and we'll put R as who eats, and then F as the food. So let's run that and see what we get. And bam. Okay, so it tells us that person 2, who is Neo, loves, so person 2 loves person 4, so loves Trinity, who eats pretzels. So here we were able to very quickly, told us what, in 23 milliseconds, it was, or 24 milliseconds, it was able to tell us, all the people who love who are crew members who love other crew members who eat pretzels. And so amazingly powerful. And we can chain those out through many, many, many chained relationships, and the efficiency doesn't really get impaired. If you compare that to what you'd be dealing with in a relational database, that could be kind of ugly because of the number of joins that you'd get into, and in some cases where a person loves a person, they're both members of the person table in a relational database, we'd be ending up doing self-joins, so we add a little bit of complexity to do a self-join on a table, and you can see the whole thing gets rather ugly pretty quickly, but it's a beautiful thing in the graph database to explore relationality to any degree of removal from the endpoints as you wish. Here's a practical example of where the unique query capabilities of graph databases are amazingly useful. Imagine that health workers are trying to contain a disease outbreak. It becomes critically important to understand who has infected whom and when. Knowing this can inform the strategies for quarantine, vaccination, and other epidemiologic steps to be taken. Again, following the chain of infection using a graph database is elementary, and the schemaless or dynamic schema nature of a graph database provides tremendous flexibility for ad hoc inquiry. Another real-world example might involve the monetization, that is, ad sales, for a popular social network. By querying a graph database, groups of like-minded or related consumers can quickly and easily be identified and selectively targeted to receive advertising messages to which they might be especially receptive. This results in a much higher conversion rate. Conversion rates reflect the percentage of time that someone looking at an ad decides to actually buy the product. Advertisers are willing to spend significantly for access to consumers who are more receptive to their message, that is, to consumers who are more often converted from shoppers to buyers. There's a famous problem in mathematics which many credit as the founding problem for graph databases, and which gives rise to numerous interesting and useful mathematical investigations into directed graphs, also known as digraphs, and the particular case of directed acyclic graphs, or DAGs. The prolific and brilliant mathematician Leonard Euler was the first to provide mathematical proof that no solution exists for the seven bridges problem. Absent Euler's mathematical genius, we can prove the same thing in a few simple steps using a graph database. Let's solve the seven bridges of Königsberg problem using some code provided by Ian Robertson, and you can look this up on the web if you're interested. Here I've got the Neo4j console open, and let's start by creating the bridges and the situation. So we'll paste that in, and you can see here that we're creating each of the bridges, and then in creating the bridges, one of the things that's a little bit funky that in the visualization engine for Neo4j, notice that there are going to be a couple of connections, two different bridges to, for example, East Königsberg or South Königsberg. When we have essentially a duplicate relationship between nodes, one gets overlaid by the other in the visualization engine. It doesn't route the arrows, but if you inspect the database, you can see that they're both there. So let's go ahead and run that and see what we get. Okay, so here's our visualization. Let's make that a little bit larger and kind of move that up where we can see it a little better. Okay. All right. And so again, even though we only see 1, 2, 3, 4, 5, remember that a couple of the bridges, there's redundant bridges to the same area of town. And so there really are two nodes there. All right. So there we are. And now that we've got the bridges in a network diagram in a graph database, what we want to do is we want to ask for the number of traverses, okay, to simulate the problem solution. And so this will ask the question, how many times do I uniquely cross a bridge in all possible different combinations? And let's run that. And we get a result. And it says, okay, you can cross 6 bridges using this route, or you can cross 6 bridges using this other route, or 6 this, or this, or this, or this, or this. So there's a number of different routes that will give you 6 bridges. Are there any that give you 7 bridges? Well, demonstrably, no, but what if we wanted to ask the question in such a way that we can show demonstrably there are no paths that exist that will allow us to traverse by these rules all 7 bridges and still meet the requirements imposed by the problem statement. Okay, so let's take a look at that. We can ask that exact question this way. So match the path relationships crossing a bridge where the length of the path, the number of traverses, is equal to 7. Can I, how can I do 7 unique bridge crossings and still meet all the criteria here? And we run it, and it says query took 39 milliseconds and returned no rows. And so that proves definitively that there are no paths that allow us to cross all 7 bridges and uniquely cross each one only once and meet all the other problem requirements. So if only Euler had this, maybe we wouldn't have some of his more brilliant mathematical theorems. He'd have just coded it up in a graph database, proved it, and moved on. This concludes the lesson.